We're going to be talking about electrocyclic reaction, which is one type of the pericyclic reactions. These reactions happen through a cyclic transition state, so in concerted fashion, no intermediates are formed. So what happened in the electrocyclic reactions, you can describe, let's say, easy as ring opening and ring closing in this reaction. So let's see. In this, here, this picture, we have a hexatriene, so 1, 3, 5 hexatriene. This picture is butadiene. And it is in that conformation so that we can make the cyclic transition state. Remember we said that's a type of pericyclic reaction, and we always have cyclic transition states in those. So it is drawn in the form of the SC's conformation to do that. Now, in these reactions, we're going to be doing the following. We're going to move electrons in a cyclic fashion, like so. In doing this, the product that we're forming, we're making now a new sigma bond here, so I'm going to draw that. So we're closing essentially the cycle. That's the new sigma bond. Let's make it bolder. Okay, and now I will have a double bond here and a double bond here. Now for the reaction below, what we're doing is the following. Now again, let's move electrons around in a cyclic form. So we're going to make this. And this electrocyclic will form a four-member ring. The following. So cyclobutene. All right, and what had happened, we had made a new sigma bond. So the overall change, notice that when we're going into ring closing, so in this direction, we have one less pi bond, so here we have 3 and here we have 2, and one more sigma bond. So overall, the change moving forward is, say, +1 sigma bond, and we have removed 1 pi bond. That's what had happened here. Here again, the same. We have formed a new sigma bond. There's 1, and here we have 2 pi bonds, and now we have 1, so 1 less pi bond. What that means in terms of enthalpy, let's analyze that. So we know that when bonds form, energy is released. So here you're forming a sigma bond, which is stronger than a pi bond. So overall, more energy is released when you form this new bond than the energy that you need to break, say, 1 pi bond, which is the overall change. Because of that, those reactions, as written in the forward direction, are exothermic. Now, again, we're talking about the cyclization, so moving in this direction. But in that direction, also, we are constraining more the molecules, so there is a decrease in entropy. So this is accompanied by a decrease in entropy. And then in terms of give-free energy, this is delta H minus T, delta S. This term, let's say, was negative, but also we have a negative delta S. So overall, this term is positive, which can cancel some of that out. So the reaction would be favorable at lower temperatures so that this term is smaller than that. If we analyze the reverse reaction, which also happens, so it would be ring opening. Then ring opening, the reaction will be endothermic, so the opposite side sign here. But entropy is now increasing since you have more degrees of freedom in the ring opening. So it is, the signs will be opposite. So here in the ring opening, you will have a positive delta H and a positive delta S. So there is a balance. This reaction can happen both ways. So now we'll be analyzing doing problems, specifically the outcome of this reaction, because there's more than one way of closing in opening ring.